to introduce Will Kirby, who will be talking about improved accuracy over classical sparse ground state solvers using a quantum computer. Take it away.
Thanks. And thanks very much for the invitation to come talk. Yeah, I'm Will Kirby. I work for IBM. And I apologize that this title is quite a mouthful, as Andrew just illustrated. But it's also going to be a little bit of a different talk. I'm not really directly going to talk about chemistry problems. I am going to talk about computational methods that are commonly used in computational chemistry. And this workshop's also on quantum advantage, so it's a bit of an ambitious talk. I hope there will be some good questions and pushback on it at the end. So just one thing to note, also since it's a chemistry talk, I can put the real classical sparse solver's name that we're talking about here explicitly in the title. We're talking about selected configuration interaction as the main target classical algorithm for this talk. Okay, also I'm going to be talking entirely in this talk about ground state approximation. So we've heard some already this morning about how actually it can be quite hard to find ground state problems that are genuinely classically hard. I'm going to hope to, we're working in that direction. That's sort of the point of this broader project. But this has also been extremely heavily studied on the quantum side. So there's a whole zoo of quantum algorithms. These are just some examples. I'm going to be focusing on these last two rows here, which are referred to as quantum SCI, quantum selected configuration interaction, or more broadly, just sample-based quantum diagonalization methods. So let me introduce what those are. The main idea in sample-based quantum diagonalization, or QSCI algorithms, is we're given a large ground state problem. It's defined by an exponential dimension Hermitian matrix. We will take some quantum circuits. We will execute those circuits, and we will measure at the end. And what this gives us is samples. If these are, for example, electronic structure Hamiltonians in second quantization, then every sample will just give us an electronic configuration. So these are the configurations in the selected configuration, if you want. We then will classically, in the pink box is a classical computer, we'll project onto this basis of configurations, and we will diagonalize within that basis to obtain an approximate ground state energy. So it's quite a simple procedure. You're using the quantum computer in some sense in the simplest way possible. We're just using it for sampling from some circuits. We're not doing any other computation than that. Everything else is handled by the classical computer. And this was first proposed in the QSCI paper from Cunesis in 2023. And there are pros and cons of doing this. The major limitation of this is that you need your ground state to be approximately sparse in order for this to work well. And the approximate sparsity is really just captured by the fact that your approximation is going to be living within this sampled configuration basis at the end. So if you don't have a good approximation, at least in energy, if energy is what you care about, of the ground state within that basis, then you have no hope. So this is sort of the minimum notion of approximate sparsity that you need for this family of methods to work. But what this buys you is pretty powerful. And it comes from the fact that this entire end of the computation is handled classically. So all the quantum computer is being used for is, again, to select this basis. So first of all, if you project out some rows and columns of a Hermitian matrix and then you diagonalize that, the resulting eigenvalues that you get will be enclosed within the spectrum of the original matrix. So you get something that is variational. And it's variational up to the precision of this classical projection and diagonalization that you do at the end. And second of all, if I run this on, say, an IBM quantum computer, and somebody else doesn't believe me that I really got the energy that I claimed that I got, I can simply give them this basis, and they can do the last step of projection and diagonalization on the configuration basis classically on whatever machine they want and trust. So if we're able to get a quantum advantage over classical methods, using this method in the sense that the energy that the quantum selected basis gives us is lower than any classical method, then this will be a verifiable quantum advantage because I can just give this basis to a third party and they can check. So to get slightly more specific, you might be wondering at this point what circuits I intend to sample from, because I've left that completely abstract up to this point. And there is a principled way to do this. This actually comes originally from analysis that was done by some folks who are sitting here in the audience on quantum Krylov algorithms. So in a quantum Krylov algorithm, there are a number of different ways to do this, but the most prototypical one I would say is you build up a Krylov basis in which you want to project and diagonalize your Hamiltonian, and the basis is spanned by time-evolved states. So you pick some time step. This defines a time grid. You build up this basis of time-evolved states, and you do projection and diagonalization within that Krylov basis. And what this gives you is very nice convergence properties, similar to Langstreth's method on the classical side. So this has been known for a while, but what we do to promote this to a sample-based method is we just sample from these states instead. So instead of doing something like a Hadamard test to estimate the overlaps and estimate the matrix elements of the Hamiltonian between pairs of these time-evolved states, which you would need to do the coherent version of the Krylov diagonalization, we're just going to sample from them. And actually that you can show that if you add one additional assumption to the assumptions that you need for convergence, you can still get a proof of convergence here. And the additional assumption that we need is this approximate sparsity condition. We need the ground state to be approximately sparse in order for this to work. The other two assumptions are the same as what you need for the ground state to converge formally efficiently for the non-sample-based algorithm. So we can call this the guided sparse ground state problem. So the guiding comes from the fact that we need an initial reference state with good enough overlap, probabilistic overlap with the true ground state, just like in phase estimation. And the sparse comes from needing the ground state to be approximately sparse. So just a quick note on the exact conditions that we need on the sparsity in order for the SKQD, sample-based Krylov quantum diagonalization algorithm, to converge efficiently. If we represent our ground state as a linear combination of configurations, and we order those such that their amplitudes are weakly decreasing, we need there to be some parameters L, alpha, and beta, such that the first L configurations, which we should think of as the important ones, carry at least weight alpha, and they all individually at least have weight beta. So in order for this to converge efficiently, we would like alpha to be close to 1, so you have most of the weight in these first L configurations. We would like L to not be too huge because we need to sample all of these things. And we need beta to also not be vanishing too quickly so that we can, again, so that we can efficiently sample all of these. So these are the conditions that we need most broadly for the SKQD algorithm to converge efficiently. But actually, from the rest of this talk, we're going to focus on the exact sparsity case. So there, we're just saying all of the weight is in the first L configurations, and we don't need to worry about the rest. So I'm going to be focusing on problems that have that structure, special case. Okay, so I'm going to spend a little bit more time motivating what we actually did before I get to what we did. And this begins by talking about the worries that we may have for this method. First worry is that, in fact, we can show that this method, this problem, the guided sparse ground state problem, is formally efficiently classically solvable. There's a truncated version of the power method. So this is a classical technique that's been around for a long time. If you add a truncation step. So you're maintaining a sparse vector representation of your iteration state at every iteration. If you add truncation so that you keep that vector sparse, and you set that threshold sufficiently high, then you can show that actually this method does formally efficiently converge. So this immediately tells us that we're in the regime of looking for what would be asymptotically a polynomial advantage at best for the sample-based Krylov quantum diagonalization algorithm. However, we're also thinking of this, at least for now, as a fairly near-term oriented quantum algorithm. So something that we'd like to execute on today's quantum processors, which means we're not really thinking about the asymptotic regime anyway. So the actual bigger problem in the existing regime is that there are a whole bunch of classical heuristics that can also work quite well for this problem. So in particular, the one I said we're going to focus on is selected configuration interaction, which I will talk about momentarily. We could also write down a truncated variant of Arnoldi's method, which is sort of the natural generalization of the truncated variant of power method. We can also do DMRG. Maybe I'll come back to this comment on DMRG at the end, and more. There are other potential methods that you could think of trying that may work well in practice. So what we'd really like to know is if there's any hope of getting towards a quantum advantage in the sense that we are running a quantum algorithm now or in the near term that simply works better for a specific problem than any of these classical methods. So it's cheaper or more accurate in some appropriate sense. We did some first experiments on impurity models using the sample-based quantum diagonalization method. And they do converge pretty well, but HCI is the heat bath version of selected CI, and that's the gray line down here. Over here, it's also sitting on top of the Hartree-Fock solution, the DMRG solution. And so what this indicates is that while we were able to find a good sparse approximation of the ground state in this case, since the SKQD algorithm worked well, in fact, that sparsity is pretty much just due to a perturbative expansion. So we have some single or core set of important states, and there is a perturbative expansion of the ground state wave function around those, and you're able to just basically chop that off and get a good approximation, since this is essentially what HCI does. So basically, we have sparsity in this case, but no classical hardness, because we know exactly how to find the important configurations to do the diagonalization in. So we'd like to understand whether we can get beyond this and how. Yeah, this is basically a couple of kind of trivial thoughts about this. It's quite challenging to actually satisfy the conditions for SKQD to be formally efficient, particularly the sparsity condition in the case of these sample-based algorithms. If you know that the ground state is sparse, then you most likely know from that at least one of the configurations that you think is important to the ground state, and then that configuration can form the initial state. So I think in practice, the sparsity condition, or approximate sparsity condition, is usually stronger than needing a good initial state. But it's quite difficult to satisfy this. And actually having this be also challenging for classical methods is difficult to find. So what we did in this project is take a sort of reverse engineering approach. I think the typical approach, which we've been hearing about some this morning, and that's been fairly commonplace in the field in the study of ground state problems, is to look within the set of problems that we care about. So we search physics, we search material science, we search chemistry, we look for the hardest problems for the classical methods, and then we try to solve them with the quantum computer, or we try to do benchmarking or resource estimates, this kind of thing. Ultimately hoping to have the quantum computer actually be useful for doing these problems that we care about. And this is a worthy endeavor. In this project, we basically inverted this order. So instead of searching within physics and chemistry for the problems that we care about, we went to try to design the physics that we need in order to get quantum advantage. And then the dream is that we use this to basically work our way backwards towards physically relevant problem instances or problem classes. OK, so that's the idea. The classical target for this phase of the project, which is the one that I'm talking about today, is selected configuration interaction. So I should say a bit about how this works. Our input is some Hamiltonian and an initial configuration. This is exactly the same input as we have for the sample-based Krylov quantum diagonalization. I initialize a pool of bit strings, or a pool of configurations with this initial one. I'm formally defining a projector onto this. And then I run an iteration where I alternate expanding the pool by applying the Hamiltonian. So people will say multiplying by the Hamiltonian, but you're not keeping track of the coherent information usually in that multiplication. You're just looking at which bit strings you reach by multiplying. We add those to the pool, and then we truncate the pool according to some cost function. So this is the cartoon of what SCI does. And then at the end of the day, we do the exact same projection and diagonalization step that we do in the quantum algorithm. So we project the Hamiltonian down onto this basis. This gives us a polynomially sized matrix, which we can then diagonalize classically. An example of the kind of cost function that we would use is this one, which is motivated by perturbation theory. So we take the ground state, the approximate ground state that we found in the previous iteration, and we look at the matrix element of the new candidate configuration with respect to that. And then there's a weighting that comes in the denominator from comparing the energies. But this numerator is really the make or break part of this, if you want. And then depending on exactly which variant you're looking at, you either keep the k most significant configurations according to this criterion, or you keep all of them above some threshold. So we would like to beat methods like this using the sample-based Krylov quantum diagonalization algorithm. And we do so by building a synthetic Hamiltonian. So how is this going to work? There's basically two main steps, which I'll talk about on the next two slides. But the big picture is we're going to take our qubits and we're going to partition them into a number of patches. Those are, in this cartoon, they're these green blocks. Within each patch, we're going to choose a path of configurations that I call S0s. So these are some states of those qubits within the patch. So for example, they might just be like the weight 1, Hamming weight 1 configurations, so single particle configurations within this patch. Then we want to engineer our interactions somehow within the patch such that our selected configuration interaction methods struggle to traverse the path, with the idea that we will give the first configuration as the initial configuration for all methods, classical or quantum. And then finally, we want to engineer interactions between the patches so that we don't have just a bunch of disjoint Hamiltonians sitting next to each other in the lattice, but we want to engineer them in such a way that the ground state of the patches and ultimately the ground state of the whole Hamiltonian is just the ground state of these paths. So these paths are forming the supports, the configuration sets that we care about finding. We would also like to do this final technical point is kind of important. We don't want this to be true for every eigenstate of the Hamiltonian. We would like this to be true for the ground state. So the ground state is just the product of the local ground states of the patches. But we would like other eigenstates to be entangled. Otherwise, actually, you can show that this is always quite trivially classically easy. So there's basically two key components to this. The first one is how we make traversing the path of good configurations difficult for SCI. And I've written a matrix here. The details of it don't particularly matter, except to note that it's almost tridiagonal. So I'm violating very slightly in the upper left corner, this just being a single path, like one talking to the next, talking to the next. In the upper left corner, the 0th configuration talks to the first two, configuration 1 and 2. But otherwise, they each just talk to the next one in the path. So this matrix is defining the Hamiltonian as projected just down onto this path of good configurations. And then the second key property of this is that if I project out rows and columns, final rows and columns of this matrix, you can check that the lowest energy state of any of these projected matrices is only supported on the first two entries. So it has zeros elsewhere. It has zeros everywhere. The ground state does. So if you think back to that cost function that I showed you before, in the numerator, we had the ground state from the previous iteration and the matrix element of that with the next proposed configuration. So the fact that these partial ground states, when we're partway through this iteration, all end with 0, means this is essentially why SCI has a really hard time converging. The ground state, if the ground state, after I have found the first 4 configurations, it has 0 in the index 3 entry, then when I try to add this configuration number 4 here, this matrix element will just be 0, because the only previous configuration it talks to is the last one. So this is true all the way up until we reach the very last row and column. And what happens when we add the last row and column is there is a level crossing such that the ground state of the entire 8 by 8 matrix is actually supported everywhere. And that's what this cartoon suggests. It's a little bit tricky to read until you know what's going on. But what this is probabilistic overlaps between the eigenstates of the ith and I plus 1th iteration, or ith and I plus 1th principal submatrices of this. So what we expect to see if the character of the ground state is essentially not changing is that, in particular, the upper left entry is just basically 1. So the ground state is just basically saying the same. It has overlap with the ground state of the next iteration. And what we see in the last step here when we go from dimension 7 to dimension 8 is that shifts down. So what was previously the ground state becomes the first excited state once we add the last row and column. So there's essentially, in the thermodynamic limit, this would be like a phase transition. Key component number 2 of this construction, how am I doing on time?
About 5 minutes formally.
Okay. Yeah. Okay. So key component number 2 is a bit simpler. If we have a larger Hamiltonian defined on our whole patch of qubits, remember that our good configurations are only a subset of the configurations of that patch. We want to control how those configurations talk to the remaining configurations of the patch. And in particular, we would like to ensure that the lowest energy state on the path, S0, which is the Hamiltonian of which is this maroon block, so that's the matrix we were just looking at. We would like the ground state of that to at least be an eigenstate and ultimately be the ground state of the whole patch. And so what we need for that is for this coupling block to annihilate that state. So acting on the ground state of the 8 by 8 block, the blue coupling block just creates 0. But it's not a 0 matrix. And then we can engineer the remaining interactions, I claim. I'll refer you to the paper for the details. We can engineer the remaining interactions such that this 8-dimensional state is in fact the lowest energy state of the entire patch. So these are the main ideas of how this construction works. what we did from there to get to some numerical and quantum experiments is to build a specific instance. So this is 49 qubits, and there's 3 patches here. I won't go too much into exactly how they're constructed, but there are these red paths. This is a heavy hex layout. This is the native layout of an IBM quantum chip. And these paths, the red path suggests the ordering of the like Hemingway 1 configurations that we use to build up the path. Every other one actually is one of the good configurations, and there are the other half of them within each path. Each path has length 16, and the other half of the configurations are the ones that the important configurations talk to at first order. So we can build a Hamiltonian that has all these properties that I've claimed that's native to this lattice, and it's up to 6 local on the lattice. So we have some non-nearest neighbor interactions, but they're bounded distance on the lattice. So we can then compile that into a quantum circuit, and we can try the classical methods on it, and we can do some comparisons. So in all of these plots, the quantum result from SKQD is the green diamonds, and so it's the same in every plot. And then each plot corresponds to a different classical method that we compare it against. So in the top, we have the good for quantum results. These are different SCI heuristics. And basically, the SCI heuristics are able to reach a certain accuracy, basically by going outside of the good subspace and then coming back. But they get stuck. And these are the best results for these heuristics that we obtained from running a very wide parameter sweep. So we were pretty exhaustively searching the parameter space for these methods. So we have the quantum being able to find the exact ground state energy by finding the exact support of the ground state, and we have the classical failing to do so. So this is where the claim in the title of improved accuracy comes from. Other classical methods are still able to solve this problem, so this is not a general quantum advantage yet. So the truncated Arnoldi method that I mentioned before is able to solve this, and it does so with a lower diagonalization dimension than the quantum does. Diagonal ranking is a fairly contrived method that we cooked up that's also able to solve this classical method, and DMRG also can solve this problem with quite low bond dimension. It's not challenging for DMRG yet. Oh, this is what I just said. Here's an example of the hyperparameter sweep for the CPC heuristic specifically. So I'm showing the energy error it's able to reach over all the different different values of the hyperparameter for this, and then also the corresponding subspace dimensions. Yeah, this is also what I just said. So these other iterative solvers that we built, plus DMRG, are still beating quantum here, so we don't have a general advantage. But we're starting to hopefully knock down. The idea is to knock down dominoes, knock down the dominoes of classical methods one at a time. The provable converging truncated power method also works. Again, I'm not going to spend a lot of time here, but it's a bit worse than truncated Arnoldi, which shouldn't be too surprising to anybody, because truncated Arnoldi is basically a direct generalization that simply captures more information, but it does also solve the problem. So I just want to spend 1 minute talking about what we've learned physically, because I claimed that was also a major purpose of this project, is to try to work our way back towards physical meaningfulness. And basically what we need for selected configuration interaction to fail is we need that for the support of the ground state, or the partial ground state that you have found at some step of the algorithm, to be strongly dependent on specifically which subset of configurations you've found so far. So in this case, we did it with just one level crossing, but you could imagine physical situations in which there's many level crossings that are controlling the ground state being locally supported on different patches of or different subsets of configurations. And this does have a name. People think about this kind of thing. This would be like compact localized states. The specific part of the construction that we used to force this property that the ground states are strictly sparse is this idea of boundary destructive interference. So in our case, that was basically coming from, this upper left block in the matrix is essentially doing the job of this. But I've drawn a cartoon here. You can show if you, this is not the matrix we used, it's just an example. But this matrix has the property that some of its eigenstates are supported only in the upper left blue block. Some of its eigenstates are supported only in the lower left red block. And some of its eigenstates are supported everywhere. And the order of these can be determined entirely, depending on the entries, by which rows and columns outside in these ellipses you actually see with the method. So looking for properties like this within physics and chemistry is the kind of thing that we're hoping to use to get us in this direction of quantum advantage for a physical problem. So with that, I'm basically done. I won't go through this summary too much. I will say that the remaining iterative solvers, the truncated Arnoldi's method and the diagonal ranking that I showed, as well as truncated power method, it's actually not too hard to tweak this to get those to fail pretty nastily in practice. DMRG is really the boogeyman here. DMRG will always be able to represent a sparse ground state because the bond dimension is that you need to represent is upper bounded by the sparsity. And in fact, in practice, for local Hamiltonians, it's usually much lower, the bond dimension. So we're never going to have a representation problem for DMRG for this class of problems. So what we're looking for here really is for the optimization landscape for DMRG to be intractable in practice. And lastly, I will just say we have this thing, the quantum advantage tracker. Whether you like or dislike the name, it does contain a lot of this problem and many more that we're using to basically try to benchmark classical and quantum methods against each other. So this problem is up there if you want to try messing around with it. We did already, there's no quantum advantage here, so you're not going to take IBM down a peg by beating this. But still, if you want to play around with it, feel free. And with that, thank you for your attention.
Yeah, I guess I have two questions. So your construction here reminds me of the constructions that were used for stochastic Hamiltonians, where there's an exponential query gap for classical simulations. Have you looked at those Hamiltonians?
No, we did specifically design these to not be stochastic because we didn't want to be subject to this type of classical attack. So no, short answer, no, I haven't really looked into it that much.
So then those things, so it seems to me what you're doing is hiding the classical support, hiding the support.
Yes.
So if you take the Hamiltonians you've constructed or that general problem, and you think of the problem of I just want to find the classical, I just want to find the support.
Yeah.
What do you think the classical complexity of that is?
So the truncated power method can solve that problem. If you give an initial state, an initial guiding state. If you don't give a guiding state, then I don't know what the complexity is. But with a guiding state, the truncated power method is formally efficient. It has a fairly nasty, at least the proof of convergence, the error bound for truncated power method depends on the inverse spectral gap cubed, which is fairly nasty. So asymptotically, one might hope to get a separation there. But yeah, as far as I know, nobody's written that down.
As far as I understand, this depends a lot on your starting state, right?
Yes.
So if you notice that your selected CI gets stuck, doesn't give you any more determinants while you expect more, could you just perturb some of your states and jump over your one barrier that you have?
Yeah. If you perturb, you need to perturb in a careful way. Okay. Otherwise, you will just jump to a random corner of the Hilbert space. And if you do that, then you're likely, in fact, since these states are sparse, you're likely to have identically zero overlap. If you go to some random other corner of Hilbert space. But yeah, if you can make, like a sensible way to make a guess would be, for example, to look at expanding under all of the Pauli terms in the Hamiltonian instead of under only non-zero matrix elements. So, all of the Pauli, sometimes Pauli terms may cancel, like an XX plus a YY does not allow transitions from 0, 0 to 1, 1. But you could, for example, look at that transition as a way to jump.
I was thinking more on the initial set of, like doing all doubles, all triples, or something like that. Would that help?
Well, in this case, it's
Or it's
there's no particular definition of singles and doubles since it's a synthetic Hamiltonian that's not an electronic structure Hamiltonian. But I could imagine, like, if you think of the Hamiltonian terms as replacing the excitation operators, then that would basically get you back to what I just said. Like, you could try expanding under the Hamiltonian terms to jump over some of these barriers.
So you said that there's no, not really, a one-to-one correspondence with like a chemistry Hamiltonian or a way to think about singles and doubles, but it is still a many-body Hamiltonian that's constructed from some single particle basis. You could imagine changing that single particle basis. Do you think that this difficulty for selected CI will persist if you are choosing a different single particle basis?
Yeah, I think essentially this will transform the whole problem in a self-consistent way. So as long as you update your initial state corresponding to the basis transformation, then the classical method should still work as long as you stay within a setting where the quantum algorithm will hurt. So for example, will work. So you could do a basis rotation that makes the ground state not sparse. And then the quantum algorithm will have no hope, and also SCI will have no hope. But if you want to preserve this as a guided sparse ground state problem, so something that SCI can tackle and quantum selected configuration interaction can tackle, then I don't think this should change the picture to change the basis.
Okay. So I kind of have two questions, but they're related, and it's sort of taking a step up.
Mm-hmm.
I'm coming from more of a complexity mathematical point of view. Is it fair to say that it's an open problem that you can prove quantum advantage for physical systems?
Yes.
Okay. And then to follow up, in basic chemistry, reactions are really about, are they not about energy transitions, not computing energies? And if that's the case, is that beyond the science? I'm just wondering if you take a step up and you say to yourself, okay, is there a way to prove quantum advantage somehow, looking at simple energy transitions with simple chemical reactions, if there's a way to approach it that way?
Yeah, I mean, I think that the talk that we heard this morning about dynamics is kind of in that direction. So on the classical side, a lot of computational methods for transitions are based on calculating energies and energy differences that you would then go into calculating a transition rate or a reaction rate. But on the quantum side, we can very much imagine doing direct simulation of a transition, like a chemical reaction. That's a different approach than this. But yeah, we may hope. There's still no proof there no formal proof of advantage, but I think that it's probably many people in the room would agree with me that I think that's a promising direction. Yeah, within this setting, I'm really just interested in understanding if there's any hope for quantum advantage for the ground state problem specifically, and specifically within this sample-based setting. But yeah, within the broader setting of chemical reactions, I think that there's a lot more levers to pull. Yeah.
Cool. I also have a couple of questions. Maybe the first one to start. Do you think that there is some hope of creating a construction like this, but where the Hamiltonian is specified as a sum of local terms, qubit or fermionic or something?
So I guess I sped through this. The Hamiltonian is defined as a sum of local terms here.
Okay. Oh, I thought it was just kind of defined as a sparse matrix.
No. It ends up being a Pauli Hamiltonian. So, sorry. Yeah. So these are it's weight 2 Paulis at most, and the distance on the graph is at most 6.
I guess the answer is yes. Then
Yeah.
there is hope.
Yeah. It's not particularly physical looking.
Sure.
Like they're non-uniform interactions around this lattice, and we're working in the direction of making it look more physical as well, basically to pull these two boundaries together. But yeah.
Sure. And then my second question, I guess if I was in a physical setting where I was maybe worried about level crossings, I would consider either a kind of state averaged approach where we try to track a low energy subspace, not just the ground state, or possibly a metropolis style update where we allow some, jumps over small energy barriers. Mm-hmm. Do you think that you can also, sort of cook up a Hamiltonian that would be proof against those approaches?
This is a really great question. I hope so, but I don't know. I think you need more. In this case, we only have a few of these sort of decoy states, if you want, like false ground states, things that appear to be the ground state when you're partway through the classical iteration. And there's not too many of them. Within each patch, there's only one. There's one level crossing that happens within each patch. Once you couple that out into the rest of the Hilbert space, you have a few more, but say only like 10. So if you were to run SCI with a 10-state block and keep all of the, where's my cost function? Instead of just looking at the ground state here, look at the lowest 10 states that you have found from the previous iteration and keep any configurations that talk to those, then I think that those would probably solve this problem. So getting beyond that, I think we need just basically a denser manifold of low energy states that can fool the classical method when it's only partway through the iteration. To the point about a metropolis style algorithm, I think that's similar to what Matthias was talking about, like considering more jumps beyond just the Hamiltonian ones generated directly by non-zero matrix elements of the Hamiltonian. Yeah.
Okay, great. Thank you.
Mm-hmm.
One last question from Garnet, and then lunch.
Hi, Will. I know in your talk you've limited yourself to non-asymptotic statements for most of the talk, but I just wanted, I've always been puzzled by a little bit of the framing in the sense that for fixed relative error in a problem, you would expect that the number of configurations you have to keep is in fact exponential in the system size. So the constraint that you only have a polynomial support seems incompatible with that requirement. So I've always been, I've always wondered why, does it make sense to have asymptotic statements at all in this? With this?
You mean essentially just because of extensivity?
Yeah, just to preserve extensivity, right? And
yeah. So this system is not really extensive.
Yeah, I understand. But in the physical simulation setting, you presumably want to preserve extensivity, right? So.
Not necessarily maybe within a material, but not necessarily within a molecule, right?
Well, a single molecule instance is, of course, you can't talk about the scaling, but one typically wants the energy of 2 molecules to be twice that of one. Mm-hmm.
Yes, I mean, so if you go towards something that looks more like a uniform lattice system, then I would expect this to stop working well. So, things like impurity models are more the kind of situation where I would.
So an impurity model is essentially a kind of dimension. There is no dimension, right? It is essentially it's always a finite problem. And okay. In that sense, So okay. So if L just there's no scaling of the physical size in the impurity model, so one doesn't require.
So, but looking at this doesn't work particularly well for a Hubbard model, for example.
Okay.
For exactly this reason. Yeah.
Let's thank Will. And,